As a result of gravimetric analysis, we got some products. These product should be named as the precipitate. These precipitate must indicate some characteristics. These characteristics are described here in this slide. The first one is the precipitates must be insoluble so as to minimize the loss of in the process of filtration and washing. These This point is actually about the stability of the precipitate. When you got the precipitate in the reaction between the solution and the precipitating agent, then the product is formed. That product should be stable enough that it cannot be further lose its integral part in the process of filtration and the washing. The second one is the physical state of the precipitate must be such like that can easily be isolated by filtration. So the precipitate should be less in number but bigger in size, that it cannot pass through the filter paper. If the number is more, if the number of crystals of the precipitate is more and the size is smaller, then they will have a large surface area and they have a greater reactivity, and they will eventually result in the colloidal solution. So when you are going to achieve a product, that product should be bigger in size and their number should be a smaller one. And the next point is the stability of the precipitate at room temperature is this is very important property, as the stability of the precipitate is very important, because the temperature if the temperature varies, then the precipitate may lose its integrity, may lose its shape, may lose its structure to again reconstitute into its anions. So its stability at room temperature is very important. And the important one is that your required precipitate must be free of contamination. No, the chances of contamination should be minimized, and the precipitate must consist of large particle that cannot clog and pass through the filter paper through the filtration during filtration process. So another aspect is to clog the filter paper. So the precipitate should be of the larger size. If they are smaller size, they may be pass through the filter paper or clog the filter paper. So in order to avoid this situation, the resulting precipitate should be in the larger crystals. So these crystals should be insoluble. These crystals should be easily processed for filtration. They should be stable at room temperature, and they should be free of contamination, and these precipitates should be large in their size, so not to clog the filter paper. In this slide, we will talk about the mechanism of the process of precipitation. The process of precipitation involves some physical and chemical processes. The first one is supersaturation. As we discussed earlier, there are three types of solutions. Number one, saturated solution, when the solution has solute up to its maximum capacity, then the solution is named as saturated solution. And if the solution has some spaces yet to be filled with the solutes, then these kind of solutions will be named as unsaturated solution. If the saturated solution, when there is no space available in the solution for dissolving the solute particles, when this saturated solution is warmed and heated, then after heating there more spaces will be available for the solution to dissolve further amount of the solute into its to adjust into its available spaces, and the solubility will be enhanced. So that solution will be known as a supersaturated solution. So when we're taking these supersaturation solution and add some precipitating agent, then there is a process of nucleation occurs. This nucleation process is actually is a starting process, a process to form a nucleus, to form a microscopic nucleus of the solid phase. It's actually the beginning of forming a bigger precipitates. When a microscopic nucleus of solid phase is formed, then the similar kind of other crystals are going to deposit on that microscopic nucleus of that solid phase. In this way, that crystals, that nucleus will go on to growth further, and a bigger crystals can be achieved in this way. So rate of nucleation is very much associated with supersaturation. It means higher rate of nucleation was recorded with the greater degree of supersaturation. If you have a less degree of saturation, then a low rate of nucleation will be observed. So in order to achieve a higher rate of nucleation, you should take a supersaturated solution for its processing. Here are some further terms to be discussed. Number one, crystal growth. After the formation of a microscopic nucleus, and after forming that nucleus, more particles will be deposited on the nucleus and forming a crystals of a specific geometric and shape. So these crystals will go on to grow to achieve a bigger size of bigger crystals of that precipitates. So after crystal growth, the induction period will be known as a time before nucleation occurs after the addition of precipitating agent to the solution. So actually induction period is a time before nucleation occurs, when you add the precipitating agent to the solution, and that moment to the point when the nucleation occurs is known as induction period. It may this induction period may in range from milliseconds to several seconds. So it means when you added precipitating agent to the solution, nucleation will start after milliseconds or several minutes. So you will have to wait depending upon the structure of the precipitate. So this induction period is very important term for the uh, process of uh, uh, precipitate formation. Then adsorption is a process in which a substance, that substance may be a gas, that may be a liquid, or maybe a solid, condenses on the surface of the solid. So adsorption is a the surface phenomena when you when you have a substance that adhere to the surface of another particle. That phenomena is called adsorption. It's parallel, another term that is absorption. Adsorption is a physical phenomena, while absorption is a chemical phenomena. So what's the crystal growth? Crystal growth is actually the formation of the deposition of smaller particles on the nucleus of the precipitate. So in this picture you can see the crystal growth. If you start from the left flask and will go towards the right side, then in the first slide in the first flask you just added the precipitating agent to the solution, and in the second slide the nucleus will be nucleus has just initiated its formation, and after that the further more and more particles will be deposited on that nucleus, and in this way a huge and large crystals of precipitate can be achieved. Digestion of the resulting precipitate, actually it involves the heating of the precipitates within the mother liquor. That mother liquor is a solution in which the precipitates are formed. So these digestion is processed for a certain period of time to encourage the densification of the nucleus. First of all, the microscopic nucleus is formed, and then the smaller particles of the precipitates are going to deposit it on the nucleus, and in this way a large crystals of precipitates are formed. So during this digestion, a small particle dissolve and large one grows. This is the Oswald ripening. Oswald ripening actually is a phenomena observed in the solid solutions that describes the change of an inhomogeneous structures over the time, that is small crystals are redeposited on the larger crystals to yield bigger crystals of the precipitate. This process helps to produce larger crystals that are more easily filtered from the solution. So, a routine, everyday example of Oswald ripening is the recrystallization of the water within the ice cream, which give you old ice cream, gritty, crunchy texture. Large ice crystals grow at the expense of the smaller ones within the ice cream, creating a coarser texture. So this digestion of the precipitate is very much important in the gravimetric analysis to enhance the size, to increase the size of the crystals of the precipitates. Okay, in this slide, we will discuss the role of von Neumann equation in precipitation process. According to von Neumann, the particle size of precipitate is inversely proportional to the relative saturation of the solution during the precipitation processes. इसका मतलब यह है कि जितना जो जो precipitate कि जो particle size है वो inversely proportional to the relative supersaturation. So what is relative supersaturation? It is equal to Q minus S divided by S. Q is a concentration of the reagent and S denotes the solubility of the precipitate at equilibrium. तो अगर आप इन दोनों की रेशो लेते हैं, ये जो आपके पास इक्वेशन आती है Q माइनस एस ओवर एस, ये हमारा हमें रिलेटिव सुपर सैचुरेशन देता है. जितना ये रिलेटिव सुपर सैचुरेशन ज़्यादा होगा उतना वॉन वीमान रेशो ज़्यादा होगा, और ज़्यादा वॉन वीमान रेशो होगा तो हमें एक्सेसिव न्यूक्लिएशन होगी, ज़्यादा न्यूक्लियस छोटे छोटे बनेंगे, और जितनी न्यूक्लिएशन ज़्यादा होगा उतना जो आपके पास प्रेसिपिटेट बनेंगे उनका साइज़ छोटा होगा और उनका सरफेस एरिया ज़्यादा होगा. एंड यू नो वेरी वेल कि जितना साइज़ किसी भी सल्यूट का अगर पार्टिकल साइज़ कम है उसका सरफेस एरिया जो है वो ज़्यादा होता चला जाता है. तो आप अगर आपके पास रिलेटिव सुपर सैचुरेशन ज़्यादा है तो जो आपके पास प्रेसिपिटेट बनेंगे वो ज़्यादा मीन उनकी क्वांटिटी ज़्यादा होगी लेकिन उनका साइज़ जो है वो थोड़ा होगा. लेकिन अगर आपके पास रिलेटिव सुपर सैचुरेशन की रेशो कम आ रही है तो इसका मतलब है कि आपके पास क्रिस्टल्स थोड़ी बनेंगी लेकिन बड़ी बनेगी. दे हैव स्मॉलर सरफेस एरिया, दे विल हैव अ स्मॉलर सरफेस एरिया. तो हमें इस इक्वेशन को अच्छी तरह अंडरस्टैंड करना है ग्रेविमेट्रिक एनालिसिस के अंदर कि अगर हमारे पास छोटी प्रेसिपिटेट बन रही हैं और ज़्यादा बन रही हैं, दैट्स नॉट गुड. आपके पास क्रिस्टल्स भले थोड़ी बने लेकिन उनका साइज़ ज़्यादा होना चाहिए, साइज़ बड़ा होना चाहिए, जिनको आप आराम से, जिनको आप इजीली फिल्टर पेपर के में से जो है कि फिल्ट्रेशन के प्रोसेस से आप सॉल्वेंट से अलग कर सकें. इस स्लाइड के अंदर दिखाया गया है कि जो रिलेटिव सुपर सैचुरेशन है उसका एक क्या इफेक्ट होता है. There are two possibilities. If you have high relative supersaturation, then you will observe the increase nucleation and formation of many small particles, which will lead you to the formation of colloidal solution. And with these small crystals, that definitely they will have a high surface area, and there are more chances of the absorption of the impurities on the precipitate. These small crystals are very hard and very difficult to wash and filter. And if you have a low relative supersaturation, then you will have a less nucleation. There are smaller number of crystals, but they are larger in size. When they are larger in size, they have a low surface area, and with a low surface area, there are less chances of the deposition of the impurities on the precipitates. So with this scenario, जो जो बेहतर इसमें से जो है वो लो relative saturation सुपर सैचुरेशन को अडॉप्ट करना होगा। उसमें छोटे छोटे न्यूक्लियस कम बनते हैं, कम न्यूक्लियस बनेंगे तो उसके ऊपर जो क्रिस्टल ग्रोथ है वो ज़्यादा होगी, और जो प्रेसिपिटेट का जो साइज़ है वो बड़ा होगा, उसको फिल्टर करना आसान होगा, उसकी वॉशिंग आसान है। जबकि दूसरी तरफ जो हायर रिलेटिव सुपर सैचुरेशन में उसका न्यूक्लिएशन तो न्यूक्लियस ज़्यादा बनते हैं लेकिन छोटे छोटे बनते हैं, कोलाइडल सोल्यूशन की तरफ सोल्यूशन चला जाता है। सो वी नीड टू मेंटेन अ क्रिस्टलाइन प्रेसिपिटेट एंड अवॉइड कोलाइडल प्रेसिपिटेट। हमें क्रिस्टल्स बनाने हैं, बड़े क्रिस्टल्स बनाने हैं, ना कि कोलाइडल सोल्यूशन की तरफ जाना है। सो ट्राई टू गेट क्रिस्टलाइन प्रेसिपिटेट विद स्मॉलर नंबर ऑफ the smaller number of the nucleus of the larger particles. So what are the conditions to process the precipitation to form a precipitate? The first one is the precipitation from the hot solution. If we increase the temperature, then the molar solubility of the precipitate will be increased. So an increase in molar solubility decreases the supersaturation and increase the size of the particle. And the second is the precipitation from the dilute solution. If you are interested to process the precipitation process from the dilute solution, then this keeps the molar concentration of the mixed reagent low. And dilute solutions are those solutions which contains the lesser amount of the solute in the solvent, so it will be known as dilute solution. So dilute solution, the slow addition of precipitating reagent and thorough stirring keeps Q, the value of Q, low. So uniform stirring prevents high local concentration of the precipitating agent. So if you have a small amount of the solute in the solution and then you reacted it against the precipitating agent, then you will have to stir it constantly. This actually prevents high local concentration of the precipitating agent. It means that precipitating agent will be reacting more vigorously when you are stirring it at constant speed. So another condition is a precipitation at the suitable pH, whether it's acidic uh, or in the basic. So precipitation should be processed at its relevant pH. If the precipitation at the pH near the acidic end of the pH range in which the precipitate is quantitative, then many precipitates are more soluble to lower, uh, it means more acidic pH value, and so the rate of precipitation is lower. So you will be very careful about selecting the acidic or basic environment of for the precipitation process. As in previous slides, the last lecture we discussed about the calcium oxalate. Calcium oxalate is stable in the basic medium. So when we change the acidity of the environment and we moved the acidity from acidic environment to basic environment, then this calcium oxalate will be in the solution form. And so it's very important to select the suitable pH of the environment as to process for the precipitate formation. Another parameter which is digestion of the precipitate. Digestion is actually depends upon the Ostwald ripening principle. Ostwald ripening is as we discussed last lecture, that Oswald ripening is the deposition of the smaller particles onto the nucleus crystal of the precipitate. In the process of digestion is actually improves the size of the structure, size of the crystals of the precipitate, and by processing this digestion of the precipitate, we will have a larger crystals of the precipitate. They will have a bigger size, but they are less in number. So these bigger in size crystals will not clog the filter paper and will not pass through the filter paper and can easily be separated from the mother liquor. When we are dealing with the gravimetric analysis, and we are going uh, for development of the nucleus to get a uh, bigger precipitate, then there are certain chances that some contaminant can be deposited on the nucleus crystal of the targeted analyte. So this process will be named as chorus precipitation, the precipitation of the contaminants, the precipitation of the contamination on along with the analyte of interest. This process is known as co-precipitation. So this process may be equilibrium or kinetically controlled. So in chemistry, co-precipitation is generally carried down by a precipitate of the substances normally soluble under the condition employed. Analogously, this co-precipitation process is specifically that the precipitation of an unbound antigen along with an antigen antibody complex. So co-precipitation is very important issue in chemical analysis, especially gravimetric analysis, when we are dealing with the crystals of the targeted analyte. So this co-precipitation process cannot be avoided. However, it can be minimized by careful precipitation and through washing of the precipitate. When we are dealing with the gravimetric analysis, there are some terms which known as occlusion, inclusion, post-precipitation, and core precipitation. These terms are usually employed when we are dealing with the impurities in the precipitation process. So occlusion is actually occurs when an adsorbed impurity gets physically trapped inside the crystal as it grows. So the impurities, the molecules of the impurities are trapped within the crystal structures of the within the crystal structure. For example, the water molecules that are trapped in the growing crystals of silver nitrate. Inclusion occurs when these actually occupies the crystal site in the crystal structure of the carrier, resulting in the crystallographic defect. This can be happen when the ionic radius and the charge of the impurity are similar to those of the carrier. And similarly, uh, post precipitation is happened when we allow the well grown crystal in the mother liquor. So when this crystal is placed in the mother liquor for a certain period of time, the contaminant molecules will deposit it on the targeted analyte crystals, precipitates, and in this way the contaminants precipitate can deposit on the precipitate of the targeted analyte, which is known as post precipitation. In this slide you can see some photographs which describes the phenomena of inclusion, occlusion, and post precipitation. The first one from the left side, top one, is the process of occlusion, which depicts the trapping of contaminant molecules within the crystal structure of within the crystal structure of the targeted analyte. For example, water molecules are trapped in silver nitrate, and the second inclusion is this process occurs when the contaminant molecule is of the same charge and size as of that carrier. So this actually occupy the crystal site in the crystal lattice. And the post precipitation, you can see in the yellow circle, when the white is actually the first precipitate, and there are some impurities which are deposited on the precipitate of the targeted analyte. Another phenomena which is peptidation, which is a process where precipitate is washed and filtered, but part of precipitate reverts to the colloidal form. इसमें प्रेसिपिटेट जो बन जाते हैं उनको वॉशिंग और फिल्ट्रेशन के प्रोसेस में बहुत सारे फिल्टर्स ऐसे होते हैं जो है वो कोलाइडल फॉर्म में आ जाते हैं। तो जो कोलाइडल फॉर्म में आ जाते हैं उसको हम पेप्टाइडेशन बोलते हैं। इस पेप्टाइडेशन को कम किया कैसे किया जा सकता है? अगर आप आइस्ड वाटर का वाटर बाथ मतलब उस सोल्यूशन को अगर आप आइस वाटर में रखेंगे तो टेम्परेचर कम करने से जो प्रेसिपिटेट का लॉस हो रहा है, जो प्रेसिपिटेट कोलाइडल फॉर्म में कन्वर्ट हो रहे थे, जो पेप्टाइडेशन हो रही थी, वो कम हो जाती है। Another phenomena which is surface adsorption. Unwanted material is adsorbed on the surface of the precipitate. तो precipitate के ऊपर किसी भी impurity का चिपक जाना, adsorb हो जाना, surface adsorption कहलाता है। इसमें digestion of the precipitate reduces the relative surface area. सरफेस एरिया कम हो जाता है, आपको पता है उसमें ओसवाल्ट राइपनिंग होती है, तो जो प्रेसिपिटेट का जो सरफेस एरिया कम हो जाता है, इट मीन्स कि वो क्रिस्टल ग्रोथ बड़ी हो जाती है। तो क्रिस्टल ग्रोथ बड़ी हो जाती है तो विच इज़ अवेलेबल एरिया अवेलेबल फॉर द एब्जॉर्प्शन ऑफ इम्प्योरिटी, तो उसके ऊपर बड़ी क्रिस्टल्स के ऊपर जो सरफेस एरिया ज़्यादा होने की वजह से वहाँ पे एब्जॉर्प्शन हो सकती है। इस सरफेस एब्जॉर्प्शन को हम मिनिमाइज कर सकते हैं बाय वॉशिंग। वॉशिंग जो है वो इम्प्योरिटीज जो ऊपर प्रेसिपिटेट के ऐड हुई होती हैं उसे हम वॉश आउट कर सकते हैं, मिनिमाइज कर सकते हैं। In order to increase the purity of the precipitate in the gravimetric analysis, we'll go for a re-precipitation process. The process of re-precipitation involves the washing away the mother liquor and redissolving the precipitate and precipitate the product again. We will take the precipitate first and then wash away the mother liquor, then pellet, that precipitate will be redissolved and precipitate again to get the purity of the crystals in at higher level. In this process of precipitation, the contamination will go away, and only the pure substance, the pure precipitate will be deposited, and the gravimetric analysis will be more fruitful with the increased purity of the precipitate. So after increasing the purity of the precipitate, these precipitate will be dried. Generally the solids are dried at 120 degrees Celsius, but the conditions for drying can vary considerably. You can choose a temperature about 65 for half an hour, or you can increase the temperature. It's all depends upon the protocol that you are following for the undertaking of gravimetric analysis. In order to dry the product of the gravimetric analysis, which is known as precipitates, these precipitates may contain some water molecules in their structure. So if you want to remove these water molecules, you will have to process these precipitates by using some laboratory equipment or instruments. You can see here the laboratory oven. It is usually known as, there are two kinds of oven. It is stagnant air. You just have a heater in the laboratory oven and you can raise the temperature up to certain limit. Different temperature limits are available in different laboratory ovens, and some laboratory ovens are hot air ovens. There is a actually a current, there is a air, hot air is moving, and that the temperature of that hot air vary up to about 200 degree, 150 degree. So it depends upon that how much temperature your protocol desires. So you can use a muffle furnace. Its temperature varies up to 1700 degrees Celsius. So it depends upon the requirement of the protocol, which equipment will suit your which will suit your protocol. So we'll use that protocol to dry the precipitate. Another example of equipment that you can use to dry the precipitate, it's a desiccator. Is commonly used in chemistry labs. These desiccators are almost usually made up of glass container, and it has a airtight lid and a perforated mesh, and beneath it it has some drying agent like calcium chloride. This calcium chloride will absorb the moisture molecule from the crystal, from the precipitate, and these desiccator will contain the dried material for the longer time as compared to simple jars and the beakers. Another method to increase the purity of the precipitate, which is the precipitation in the presence of electrolyte, coulombic repulsion, जो कि electrostatic charges होते हैं, they are diminished in the presence of electrolyte because of a compression of the volume of the ionic atmosphere. Then the next method to purify the precipitate is digestion. If we raise the temperature of the colloidal solution, they will increase the collision energy of the colloidal particle and overcome the coulombic repulsion, leading to the formation of larger particles. इसमें हम क्या करते हैं कि सॉल्यूशन को गर्म करते हैं, टेम्परेचर बढ़ाते हैं. उस टेम्परेचर बढ़ने से जो कोलाइडल सॉल्यूशंस होते हैं, कोलाइडल पार्टिकल्स होते हैं, दे विल कोलाइड, उनकी कोलिजन एनर्जी बढ़ जाती है और उनकी जो आपस में कोलम्बिक रिपल्शन होती है, आपस में जो फोर्स ऑफ रिपल्शन है वो कम हो जाती है, वो ओवरकम हो जाती है, और वहाँ पे लार्जर पार्टिकल्स जो हैं वो बनना शुरू हो जाते हैं. Okay, we are coming to the calculations after performing the precipitation process. impurities को हमने कम किया, purity को हमने increase किया. तो अगर हम इसको सारे प्रोसेस को रिवाइज करें, उसमें हम देखें कि सबसे पहले हमने सोल्यूशन बनाया. सोल्यूशन जो हमारे पास सैम्पल सोल्यूशन था, जो हमारा एनालाइट जिसको हम एक्सट्रैक्ट करना चाह रहे थे, रिकवर करना चाह रहे थे, प्योर करना चाह रहे थे, उस सैम्पल सोल्यूशन को हमने रिएक्ट करवाया विद द प्रेसिपिटेटिंग एजेंट. प्रेसिपिटेटिंग एजेंट के साथ रिएक्शन के साथ वो वहाँ पे जो है हमने कुछ देर उसको इनक्यूबेट किया एट सूटेबल टेम्परेचर, और उसको हम स्टेयर भी करते रहे साथ साथ जब हम सैम्पल सोल्यूशन को और प्रेसिपिटेटिंग एजेंट को मिक्स कर रहे थे. तो इस कंटिन्यूस स्टेयर के अंदर हमारे पास प्रेसिपिटेट बनना शुरू हो जाते हैं. उससे अगर प्रेसिपिटेट तो फौरी बन गए, डेट्स वेरी गुड. अगर नहीं बने तो यू मीन विल गिव इंक्यूबेशन. उससे आप 0 to 24 आवर और सम टाइम आई मीन हायर देन 24 आवर, ग्रेटर देन 24 आवर्स आप दे सकते हैं. उसके बाद जब प्रेसिपिटेट डेवलप हो जाते हैं तो उस प्रेसिपिटेशंस की आप डाइजेशन करते हैं. डाइजेशन में ऑस्टोवाल्ट राइपनिंग होती है, क्रिस्टल की ग्रोथ हो जाती है, न्यूक्लिएशन होती है, और जब क्रिस्टल्स बड़ी हो जाती हैं आप उसे हार्वेस्ट करते हैं, आप उसे फिल्टर पेपर के ज़रिए अलग कर लेते हैं. सॉल्वेंट अलग हो जाता है और जो आपके पास जो प्रेसिपिटेट आए थे वो अलग हो गए. अब उन प्रेसिपिटेट को आपने जो अलग कर लिया उसको आपने वॉशिंग दी ताकि वहाँ से जो इम्प्योरिटीज़ हैं वो रिमूव हो जाएं. अब इम्प्योरिटीज़ को वॉश करने के बाद आपने जो आपके पास प्रेसिपिटेट थे उन प्रेसिपिटेट को आपने हॉट एयर ओवन के अंदर ड्राई किया. तो ड्राई जो 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 टेम्परेचर है वो डिफरेंट होता है डिफरेंट प्रोडक्ट्स के लिए, और टाइम भी डिफरेंट हो सकता है. आई मीन आधे घंटे से समटाइम 70 मिनट, 80 मिनट, समटाइम 15 मिनट में, वो डिपेंड करता है कि मॉइस्चर कितना ज़्यादा है उस प्रेसिपिटेट के अंदर। तो ये जब आप ड्राई कर लेते हैं तो ड्राई करने के बाद फिर आपने बहुत ही प्रिसाइसली आपने जो आपके पास प्रेसिपिटेट है उसका आपने वज़न करना है, उसको आपने वे करना है। वे करने के लिए यू विल यूज़ एनालिटिकल बैलेंस, कैलिब्रेटेड होना चाहिए एनालिटिकल बैलेंस। और जो आप वज़न कर लेंगे उस वज़न में आप एक फार्मूला जो है वो लगाएंगे, जिसमें फार्मूला वेट ऑफ द एनालाइट जो कि ग्राम पर मोल में होता है डिवाइडेड बाय फार्मूला वेट ऑफ द प्रेसिपिटेट जो आपने प्रेसिपिटेट निकाले हैं, मल्टीप्लाई बाय मोल एनालाइट, एनालाइट की कंसंट्रेशन क्या है और प्रेसिपिटेट की कंसंट्रेशन क्या है। इस जरिए से आप इसको जो है वो आप ग्रेविमेट्रिक कैलकुलेशन जो है वो कर सकते हैं। This slide describes you the advantages of gravimetric analysis. This gravimetric analysis is very accurate and precise when using modern analytical balance, and possible sources of errors are readily checked, since filtrates can be tested for completeness of precipitation, and precipitates may be examined for the presence of impurities. So this gravimetric analysis is an absolute method. It involves direct measurements without involving any form of calibration, and then the determination can be carried out, which relatively inexpensive apparatus. The most expensive items are muffle furnace and sometimes platinum crucibles. Otherwise, the overall glassware and the apparatus used in the gravimetric analysis are inexpensive. So gravimetric analysis are used to determine the atomic masses of many elements to six-figure accuracy. And similarly, gravimetry provides a very little room for the instrumental error and does not require a series of standards for calculation of an unknown. Despite some advantages of gravimetric analysis, there are some precautions that need to be addressed. That proper lab technique is critical. It is very careful. It requires very careful dealing, and it is time consuming. And careful glassware cleaning, as if there exists some impurities in the glassware, that impurities present in the glassware can affect the gravimetric analysis. So it is very important to wash the glassware very carefully with distilled deionized water in the final step, to remove all the associated ions and the debris. It requires very accurate weighing. For this you need to have analytical balance of high accuracy, and then the co-precipitation is a common phenomena which decreases the impurity of the precipitate. So in order to avoid to get a high purity precipitate, you need to minimize the chances of co-precipitation. In this slide we will discuss the estimation of barium ion in a given solution by employing the gravimetric analysis. This protocol, this experiment will require the following chemicals and apparatus, which for example barium chloride, potassium chromate, distilled water, concentrated HCl, funnel, flask, beaker, and analytical balance and hot air oven. And the principle of this gravimetric analysis is, when the barium chloride solution is mixed with the potassium chromate, then the barium ion of the barium chloride will react with the chromate ion of the potassium chromate. Then the barium chromate will be formed the color of that precipitate of the barium chromate is yellow color, and yellow color precipitate will settle down under the force of gravity. And the equation is given here in this slide. And if you want to discuss this procedure, you just take 50 ml of the barium chloride solution in a flask, and then add 1 ml of concentrated HCl to enhance its solubility. After heating, excessive amount of potassium chromate will be added to the to the analyte solution. And when we add these chromate solution into the barium solution, immediately the yellow color precipitate will start to form. So when we added the potassium chromate in the barium chloride solution, we continuously shaking the reaction mixture, and after a few seconds, almost immediately, yellow precipitates of barium chlorides will be appeared. And we still are adding potassium chromate in excess amount in order to grab all the available barium ion into the barium chromate. So these yellow precipitates that will be collected in the bottom of the filter, in the bottom of the container. These precipitates will be collected, and will be collected using the process of filtration. We will use a filter paper of suitable size. After collecting these yellow precipitates of barium chromate, these precipitates will be freed from the moisture, from the water molecules. Water molecules will be removed by placing it in a air dried in a air dried hot air oven. And the weight was the net weight of the precipitate was achieved, and the calculation by using calculation was made. So for example, the net weight of the precipitate was estimated to be 0.4 gram. This is a case study. We process this experiment in the lab, and these are the results of our lab experiment. We have a 0.40 gram of barium chromate, and the end point of what would be the end point of this barium ion estimation experiment. Actually, the gravimetric analysis includes some indicator which are precipitate indicator. When the formation of precipitates, actually it indicates the completeness of the reaction. So the appearance of yellow precipitate will show you the completeness of the experiment, and this will be taken as the end point. The net weight of the precipitate was 0.40 gram, and then the molecular weight of barium chromate is 253.3 gram. So barium chromate contains barium ion, it's 137.3, its atomic weight of barium. So our product, that is 0.4 gram of barium chromate, contains barium ion. It's it's gonna be 0.217 gram. So this solution that we took in the earlier stage, that was 50 ml of barium chromate solution, it contains barium 0.217 gram, and we apply the unit method. So 1 ml of barium chloride solution contains, you can simply divide, and if you want to calculate in 1 liter of the barium chloride solution contains barium ion, so then you will simply apply a simple mathematics, and you can see here in this slide the total the concentration of barium ion in a given solution is 4.37 gram per liter. So these are the calculations which were involved in estimation of barium ion in a given solution by using gravimetric analysis.